Welcome to the Chapter 11, Part 1 notes. We are starting this chapter, which is an introduction to calculus. So I changed the format of the notes so that you can have these as a reference as you're working through calculus. I have also included an introduction about what calculus is, where it comes from, the history of calculus, some famous people who helped develop the study of calculus, and a little bit about why calculus is important. So you can choose to read through that on your own time. We are going to jump in with some vocabulary that will be really important in order to understand what's called the tangent problem. And the goal for this section is to build up to the derivative, which is a foundation of calculus. Okay, so in this section, we're looking at derivatives. In the next section, we'll be looking at what's called the integral, which is the opposite of a derivative. Okay, so some vocabulary to know. The first term, rate of change, we use usually for lines when we're talking about the slope of a line, but we can also find a rate of change for any function just by finding the slope of the line that would connect those 2 points. So when we're talking about a rate of change, if we talk about it as a slope, that can only be used for linear functions. If we're talking about the rate of change of a non-linear function, we have to call it by its full name, rate of change. Velocity is a vector representing speed. So velocity and speed are often used interchangeably, but velocity also means that there's a direction that it's traveling. Okay, so speed is usually just the magnitude, and velocity includes the magnitude and direction. When we're solving for velocity, we are almost always solving for a speed. So even if we're given the direction of the speed, when we're being asked to solve for velocity, we're looking for things like miles per hour, feet per second, meters per hour. It could be any speed as a distance over time. To find the instantaneous velocity, that's looking at the speed essentially at just a specific given time. And since speed is described as distance over time, if we're looking at an instantaneous velocity, that's looking at a time where the change in time is 0. So there's a very special way that we approach finding what's called the instantaneous velocity. That's our first couple examples. Okay, the other terms that we'll need to know are from geometry. The first term is tangent. In geometry, when we talk about tangent, it's a line that touches a circle at only one point. And specifically, if we think about a tangent line, we're thinking about if I was standing on the function, what kind of slope would I be standing on? Okay, so not a slope that passes through the function, but the slope that kind of bounces off or is parallel to where the function is at that just one point. And then the secant line is a line that goes through 2 points. So that's the important distinction here between tangent and secant. Tangent is looking at just 1 point. Secant is looking at 2 points. Okay, now there are some other terms from geometry that I included in this image, but those are the two that I want to focus on, tangent and secant. Okay, so let's look at it, our first example. In our first example, we're looking at how do we find velocity or speed. The velocity is distance divided by time. So in example 1, an automobile travels 120 miles. That's going to be our distance. In 2 hours and 30 minutes, there's our time. We want to find the average velocity over the entire trip. So velocity equals distance over time, and really it's change in distance. So we use a capital delta to represent change, just like we did for slope, right? When we were looking at slope, it's change in y over change in x. Same thing for velocity, we're looking at the change in distance over the change in time. So how far did we travel and how long did it take? So our distance is 120 miles. Our time is 2 hours and 30 minutes. Now notice that's 2 different units, hours and minutes. We want to convert everything into the same units. You can choose hours or minutes. It doesn't make a difference here. Because we usually think of miles per hour, I'm going to change this into hours. So 2 hours and 30 minutes is 2.5 hours. So to find our velocity, we take our distance, which was 120 miles, divided by our time, which is 2.5 hours. 120 divided by 2.5 gives us a value of 48 miles per hour. MPH for miles per hour. You can write this as 48 miles per hour means the same thing. Per means division. Okay. Now, just because we traveled at an average of 48 miles per hour does not mean we were traveling 48 miles per hour the entire trip, right? So if I were to graph my, my trip, time and distance, I know that at time 0, I had not traveled. So I'm at 0 time and 0 distance. And we know at 2.5 hours, we have traveled 120 miles. Those are the only 2 data points we have. So we don't really know what's happening between those 2 points. It could have been a constant speed of 48 miles per hour. That's a possibility. When we're talking about driving, though, we don't start driving at 48 miles per hour. Usually we start out slower, we work our way up, maybe we get on the freeway and we go a little bit faster for a while, and then we hit the exit ramp and we slow down. Okay, so just because those are the 2 data points we have does not mean that the function is connected between those points linearly. It just means that something is happening between those points, and the average of all of those slopes gave us 48 miles per hour. If I wanted to know what speed I was going at, let's just say 1 hour, okay, I cannot assume that I was traveling 48 miles per hour 1 hour into my trip. In order to find the speed at that exact time, I would have to find the point at that time and somehow find what my speed or slope was for that one point in time. And that's what we're going to look at in our next example. Okay, when we're looking at a speed at just one given time, there's not a range of times, there's not a change in time. So we would have to divide by 0, which we cannot do. So how we go around that is we use limits. And it's the same limits we've seen in previous chapters, but this is going to be a new application of those limits. Okay, so let's do a quick review of limits. When we're talking about limits, we're talking about not what's happening on a function at a given point, but around that given point. So the limit as x approaches 5 of f of x means what are the y values around the x value of 5. So 4.7, 4.8, 4.9, 4.95, 5.1, 5.05. We're looking at the values that are close to approaching 5, okay? If our graph is continuous, those values will also approach f of 5. However, if our graph is not continuous, remember it could have been approaching a number and then made a jump, or there could be a removable discontinuity. We could approach a value and then the function is not defined at that point. Or it could be asymptotic. We could be approaching infinity and our function is undefined at a value. Okay, so if our function is continuous, we can say that the limit as x approaches 5 of f of x will equal f of 5. That was our definition of continuity. If it's not continuous, we can still calculate the limit. So let's look at example 2. We have a ball that rolls down a ramp. Okay, so we have s is our distance from the top of the ramp after t seconds, and we're given that the function that produces is t squared. So what is the distance the ball has traveled after t seconds? Distance was s, and we're looking at distance over time. So distance is directly related to time. So we can say s of t equals t squared. Okay, our distance was measured in feet, and our time is measured in seconds. So time is in seconds and distance is in feet. Second part of the question, what is the average velocity of the ball over the first 2 seconds? So our change in time is 2 seconds. Specifically, we're going from 0 seconds to 2. We can say our interval of time is from 0 seconds to 2. And then we need to also find our change in distance? Well, we're not given that information, so we need to find it. I've provided this graph of t squared where we can see at time 0, our distance is 0. So at time 0, our distance at time 0 is 0 squared, which is 0. Okay, so our time and distance both start at 0. I'm going to label it as 0, 0. And then for time 2, to find the distance, we're looking at distance at time 2, which is 2 squared, which is 4. So at time 2, our distance is 4. That means our interval for distance is from 0 to 4, giving us a change in distance. 4 minus 0 is 4. So our average velocity, change in distance over change in time, right? Miles per hour, distance over time. Okay, so our change in distance was 4 minus 0. Change in time was 2 minus 0. We already calculated these as 4 over 2, which gives us 2. 2 what? Velocity has the measurement of speed, so it should be distance over time. Our distance was in feet, and our time is in seconds. So that's 2 feet per second. Okay, so the average velocity, the average speed of the ball over the first 2 seconds is 2 feet per second. In 2 seconds, the ball traveled 4 feet, so the average is 2 feet per second. What about the velocity or speed of the ball at 2 seconds? So at the end of our 2-second interval that we measured, what is the speed of the ball? Well, it's not 2 feet per second because that's the average over the whole first 2 seconds, and it started out slower and it's gaining speed. So I would expect my instantaneous velocity, my speed at 2 seconds, to be higher than 2. Okay, but how do I calculate exactly what it is? Well, imagine, oh, I did that backwards. Here is our graph of t squared. Okay, let's say that this is 2 seconds. In order to find out the exact speed at 2 seconds, I can look at what are my speeds approaching. So if I look at all of these speeds approaching from either direction, I can get a good idea of what's going on at exactly 2. That is what a limit means. I'm going to look at the average speed over smaller and smaller intervals until I can say, well, if I kept going, the pattern shows that this is the number that I'm approaching. So we say our change in t, we want to know at exactly 1 time. So our change in t would be 0. And at a given time, the distance isn't changing, right? The marble or the ball would be stagnant at just 1 screenshot of time. We can't do 0 divided by 0. So then the limit as time approaches 0 of our change in time over change, or change in distance over change in time, is going to be, for any of these blue points, I can say at that time, my distance is t squared. And we're going to look at what happens as that t gets closer and closer to 2, which has a distance from the start of 4. Okay. So my change in time is getting closer and closer to 0, meaning my t is getting closer and closer to 2. The limit as t approaches 2 of, okay, so then how do I find my change in distance? Well, before we saw that was a change in distance is the difference of the y values. So my y value here, I start at a y value of 4, and I stop at a y value of t squared. So whatever the blue point is, t comma t squared. Divided by, how about my change in time? Well, I'm looking at the distance from 2 to whatever time, t. So if I'm looking at this, now I have only one variable, and that variable is time. And the goal is to get time as close to my end point as possible, as close to 2 seconds as possible. So now we have an equation here. and we can try to simplify. I have a fraction. To simplify a fraction, I need to factor. So to factor this, I can look at the limit as t approaches 2 of 4 minus t squared is a difference of perfect squares. That's 2 squared minus t squared. 2 minus t times 2 plus t divided by 2 minus t. We can simplify that. So we end up with the limit as t approaches 2, because that's what we want to know. What's happening as the ball approaches 2 seconds? What is their speed at 2 seconds of 2 plus t? Okay. Now, if this function is continuous, I can just go ahead and substitute that 2 in for t. 2 plus 2 equals 4. In this case, it works for what? 4 feet per second. So that means my slope at 2, the tangent line when time is 2, has a slope of 4. If I go back in time, that slope will be slightly less. If I go forward in time, that slope will be slightly more. Okay. So if we're looking at the instantaneous velocity, we have to set up a limit. So let's take a closer look at finding this instantaneous velocity for other points on this same graph. In our next example, we're looking at finding the limit of the graph at the point 2, 4, which we already kind of looked at, and a new point 1, 1. And the reason we want to look at this separately from the last problem is we're looking at how do I do this if I don't calculate the average velocity first, okay? And the key here is that we're looking at the average rate of change as our distance between the points gets smaller and smaller. So on the last example, what we said is if I look at the point 2, 4, and I look at the distance or the average rate of change while the points are farther apart, it's going to give me an average slope that's not necessarily close to the slope at a specific point, the instantaneous rate of change or the instantaneous velocity. If I get closer, as the point gets closer, my approximation will also get closer. So we're looking at the limit as those points get closer and closer and closer. And eventually, those points will be so close that there's practically no space between them. And that's when we will find our slope of the tangent. Okay, so how do we do that? Well, we take our point 2, 4, and we take an arbitrary point, any point on the graph, and we use, didn't mean to erase the 2. What's happening? There we go. Okay, an arbitrary point. Using our function, we can say whatever time t is, our distance is t squared. And we find the slope between these 2 points. And then we take that point and we move it closer and closer. That's what the limit does. So the first thing is to find the slope between those 2 points, the slope of the line between the 2 points. So we find the change in y over change in x. That's, I can do t squared minus 4 or 4 minus t squared. Both of them will give me the change in y divided by, if I did t squared first, then I have to do t first. Okay, and then to move the point closer and closer to my desired point, I'm going to find the limit as t approaches 2. T squared minus 4 divided by t minus 2. And then we want to see if we can simplify. Can we simplify? Indeed, we can. We can factor our numerator, the limit as t approaches 2 of t plus 2 times t minus 2 divided by t minus 2. This should feel familiar. It's almost exactly the same process we just did. All I did was show you that it doesn't matter which x and y value we choose first, as long as we choose the same value or the same point to take those values from. So then we have the limit as t approaches 2 of t plus 2. Now the limit means what's happening as t gets closer and closer and closer to 2. So we want to look at what's happening when t is 1, when t is 1.5, when t is 1.75, 1.9. But we can see that this graph is continuous, so we know that that value that it approaches will be when t is 2. So actually, let me say, this graph is continuous. So this equals when t is 2. So then we can say when t is 2 plus 2 is 4. We already saw, we knew that was going to be the answer. So the slope of the tangent line is the same as the instantaneous velocity, the instantaneous rate of change. Okay. What about for the point 1, 1? So now here's my point. 1, 1. And we're going to choose an arbitrary point, t comma t squared. And we're going to make that point get closer and closer and closer until we can find the slope at 1, 1. So first, let's find the slope between these 2 points. Change in y over change in x. I like to put the variable first, but it's up to you. You could do 1 minus t squared or t squared minus 1. Change in y, and then my change in x. If I started with the variable, I start with the same point, but the other coordinate. And then we're going to take the limit as t approaches. This time, t is approaching 1, because that's the x value that I want to approach. I'm going to factor t plus 1 times t minus 1 over t minus 1. Simplifies. So this equals the limit as t approaches 1 of t plus 1, right? Now, because I know that this graph is continuous, I can go ahead and just substitute t in. So this is 1 plus 1. So I just substituted this value in for t. Because the graph is continuous, this is 2. Now I don't have units because I don't know that this is a velocity. All we're doing is we're finding the slope. Slope does not have units. Okay. So if I knew that this was a velocity, if we were still talking about the question question in example 2, then I would say that this was in feet per second. But we don't know that. We're just finding the slope of the line tangent to the point 1, 1. Okay. So how does this relate to calculus? Well, if we can find the instantaneous rate of change or the slope of the tangent line, that is what in calculus we call the derivative. Okay. So when we're looking for the derivative of a function, we can look at the derivative of a whole function, or we can look at the derivative of a function at a given point. Okay. What we have been doing so far is finding the derivative of a function at a given point. So we've already been finding derivatives. Okay. The way derivatives work is we first look at the average rate of change, right? That's what we were looking at in our last example. We started by finding the slope between 2 points. The average rate of change is the slope of the secant line. And then we said, okay, if we get those points close enough together, we can see what's going to happen when they become the same point. And that's the derivative. The limit as x approaches a of our change in y values, f of x minus f of a, divided by our change in x values, x minus a. Okay. The formal definition in calculus is this equation right here, where I choose to have x minus a be called h. Okay, so this is essentially, we just said let h equal x minus a. Then h is always going to be approaching 0. The distance between x and my goal is getting closer and closer to 0. So we have f of a plus h minus f of a all divided by h. Okay, so essentially anywhere there was an x, we replaced it with, if h is x minus a, then x is h plus a, or a plus h. Okay, so we replaced all of the x minus a's and x's so that we have only h and a. Okay, to denote a derivative, we can use an apostrophe, and we read that apostrophe as prime, f prime of a. So f, it looks like just f of a, but it has this little apostrophe. That means the derivative, f prime of a. Is same thing if we're finding the derivative of a whole function, we would say f prime of x, because we would leave x as a variable. Okay, so let's go ahead and take a look at example 4. In example 4, we want to find f prime of 4 for the given function. So we want to find the limit as h approaches 0 of f of, we need to know what our a value is, right? A is 4. So f of 4 plus h minus f of 4 divided by h. All I'm doing is I'm substituting a into my definition of a limit. And then I need to find what is f of 4 plus h. And I'm going to need f of 4. So f of 4 plus h, everywhere there was an x, I substitute 4 plus h into my function. 2 times 4 plus h squared minus 3. 2 times 4 plus h squared is 16 plus 8h plus h squared minus 3. I'm going to give myself a little bit more space. Equals 16 times 2 is 32 plus 16h plus 2h squared minus 3. Putting it into descending order, that's 2h squared plus 16h plus 29. And then we also need f of 4, which is 2 times 4 squared minus 3. 16 times 2 is 32 minus 3, which is 29. So into here, we put the limit as h approaches 0 of f of 4 plus h we found, and that is 2h squared plus 16h plus 29 minus f of 4 minus 29 divided by h. 29 minus 29 is 0. The limit as h approaches 0, I have an h in both terms, so I can actually factor out h. 2h plus 16 divided by h reduces again. The limit as h approaches 0 of 2h plus 16. Okay, this is a quadratic function, so we know it's continuous. So we can say 2 times 0 plus 16 equals 16. Okay, so our total here, the whole process, we started with our equation, we substituted into the function from the equation, and then we solved for the limit. For our last example, we're going to do the same thing. So our formula, the limit as h approaches 0, f of a plus h minus f of a divided by h. Now we're finding the derivative of a whole function. So we're not substituting in a value for a. We're substituting x essentially in for a. So we want f of, oh, I forgot my limit. Limit as h approaches 0 of f of x minus, it's supposed to be a minus, right? Nope, plus h minus f, there's the minus, divided by h. What is f of x plus h? Substituting x plus h in for x, we get x plus h squared minus x squared divided by h. Don't forget to FOIL the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. So then we get the limit as h approaches 0, x squared minus x squared goes away. Factor out an h times 2x plus h over h. You'll notice that an h almost always factors out, equals the limit as h approaches 0 of 2x plus h. We know that x squared is continuous, so I can substitute a 0 for h, so we get just 2x. The reason we have an x in our answer is because we had x as our variable for a. If we had a number, we would have ended up with a value there. Okay. And then the last one, we want to find dy dx. That's just another way to say the derivative. So dy dx is the same as f prime of x. So we want to do the same thing, but now our function is 1 over x. So we have the limit as h approaches 0, f of x plus h minus f of x divided by h. The limit as h approaches 0, 1 over x plus h minus 1 over x, all divided by h. The limit as h approaches 0, I'm going to write it as 1 over h times, and I'm going to combine a like denominator of x times x plus h is my LCD. So that's x minus x plus h divided by x times x plus h. That gives me the limit as h approaches 0, x minus x goes away, so this becomes negative h divided by h, x times x plus h. Cancel the h's. So this is the limit as h approaches 0 of negative 1 divided by x times x plus h. Okay, now here's the trick. 1 over x is not continuous. Okay, however, we can still substitute h in as long as we say that x cannot equal 0. So we're going to substitute negative 1 divided by x times x plus 0, which is negative 1 over x squared, where x cannot equal 0. Okay, so essentially we found the derivative, but there was a condition. Since 1 over x is not continuous, we have to say that x cannot be 0. Okay, we'll do more practice on this together in class, but that's kind of our first introduction to putting all of this together for calculus.